Problem number 19. A cavity of radius r over 2 is dug out of a spherical planet with a uniform mass density of mass m and the radius r. What is the magnitude of the gravitational field at point P in the diagram below? Solution for problem number 19. Solution for this problem could be created using vector form. Let's draw this picture with a gravitational field for full sphere is E1. Gravitational field for part of this sphere is E2, and E is gravitational field for our figure with the cavity. So it means that E1 equal E plus E2, and from here we can find that gravitational field for our figure with the cavity equal vector E1 minus vector E2, or using cosine form for vectors we have this form where theta, that's the angle between vector E1 and E2. Now we can write that E1 equal G multiplied by mass over R square, E2 equal G multiplied by mass of small sphere, which is m over 8, divided by 5 over 4 r square, where distance from center of this small sphere to point P equal square root from 5 over 2 r. And we have E2 equal 1 over 10 g m over r square. And for angle theta we have cosine theta equal 2 over square root from 5. Now we have E square equal this expression, which is 0.831 E1 square, or finally we have gravitational field equal 0.912 gm over r square. That's answer E, and that was solution for problem number 19. Problem number 20. The line between day and night on a planet or moon is called the terminator. How fast does the terminator of Earth's moon move across its surface at the equator? The radius of the moon is 1.74 multiplied by 10 power 6 meters. Solution for problem number 20. The same side of the moon always faces Earth. This means the terminator runs all the way around the moon once per month. So the speed equal 2 pi multiplied by radius of moon and divided by 28 days, which is approximately 4.5 meters per second. This is answer B, and that was solution for problem number 20. Problem number 21. A solid sphere sits at the top of a ramp of a height h inclined at angle theta to the horizontal. Both the static and the kinetic coefficients of friction between the sphere and the incline are mu k equal mu s equal 0.2. The sphere is released from rest at the top of the incline. For which of the following values of theta is the total translational plus rotational kinetic energy of the sphere greatest when it reached the bottom of the incline? Solution for problem number 21. The maximum translational and rotational kinetic energy possible when the motion of sphere is without sliding. In that case, force of friction doing zero work, and the whole gravitational potential energy turning to kinetic energy for translation or rotation. It means that we have to find the critical angle for which this is possible. Let's write two equations for translation and rotation. For translation we have ma equal mg sine theta minus force of friction F. For rotation we have I alpha equal Fr. For solid sphere, moment of inertia I equal 2 over 5 mr square. And the condition for sliding give us angular acceleration alpha equal acceleration a over radius of the sphere r. Let's put this to the second equation. We will get that force of friction will be equal to 2 over 5 ma. We can put this to the first equation and define what is acceleration. That will be 5 over 7 g sine theta. And now we can calculate what is force of friction. Force of friction will be 2 over 7 mg sine theta, which cannot exceed maximum possible force of friction, which is mu multiplied by normal force, which is mg cosine theta. And from this inequation we can find that tangent theta must be less or equal to 7 over 2 mu, which will give us a critical angle 35 degrees. For angles less than 35 degrees, we don't have any energy loss. It means that the correct answer is A, 10 degrees. And this was a solution for problem number 21. Problem number 22. A ship rams into a hunk of ice floating in the sea. Icebreakers are ships designed so that when this happens, the ice is pushed down beneath the ship. If the coefficient of static and kinematic friction between the ice and the ship is mu, what condition applies to the angle theta as shown in the figure, so that the icebreaker functions as intended. Solution for problem number 22. There is a force from the ship on the ice, which may be broken into a normal force and a friction force. The vertical component of the normal force is negative n multiplied by cosine theta, and the vertical component of the friction force is F multiplied by sine theta. The friction force can be at most mu n, so the vertical force from the ship on the ice is Fy less or equal than mu n sine theta minus n cosine theta. And from here, because force Fy must be less than 0, we have cotangent theta must be greater than mu, which is answer A, and that was a solution for problem number 22.